Now that we hopefully all have a at least basic understanding of monads and how to write monadic code, either by using explicit bind and return or by using do notation, we can look at a very important monad for Plutus, namely the contract monad. And maybe you have already seen that in the code examples I provided. So the contract monad defines code that will run in a wallet. So that defines the off-chain part of Plutus and is equally important to the on-chain part. But before we go into details with this contract monad, I also want to talk about a second monad, so-called EmulatorTrace monad, because quite a few of you asked me whether we really need the playground to test Plutus contracts and whether there's a quicker, easier, and faster way that doesn't require you to start this playground server and then always manually copy paste over into the editor and so on. And there is indeed, and this is done via this EmulatorTrace monad. And you can think of a trace in this monad, a program in this monad, as what we do manually in the simulator tab of the playground. So there we always define the initial conditions and then defined action. So we said wallet 1 does this, invokes this endpoint with these parameters, and then we wait so and so many slots, and then wallet 2 does this, and so on. And things like that you can also do in this trace monad. So we should look at that first. Emulator traces are defined in module plutus.trace.emulator in package plutus-contract. And we see that emulator trace A is a type abbreviation, type synonym for some very complicated looking effect monad. This is what I mentioned before, that the Plutus team used so-called effect system to build custom tailored monads, including this emulator trace monad. But we don't have to worry about that, what that means. So before we look at how to define traces, let's first look at how to run them. And the most general way is this run emulator trace. So it takes an emulator config, we will look at that in a minute, and a trace with unit result, and then produces a triple. And note there is no IO here. So that means this run emulator trace is a pure function. It's a pure function without any real world side effects. And this triple, so it's a list of emulator events, then maybe an emulator error. So if there's no error, that will be nothing. And if there is an error, it will be just the error, and some emulator state. So let's first look at the config, the emulator config. And we see it's a record type with 3 parts: an initial chain state, slot config, and a fee config. Let's look at the initial chain state first. That's either an initial distribution or something called TX pool. So an initial distribution is a map from wallet to value. So it specifies what wallets you have and how much initial funding they have. Let's see what this TX pool is. That's just a list of transactions. So you can basically specify a list of transactions that have happened before the simulation, before the emulator trace starts. Okay, that's the first component of this record. The second, the slot configuration, is about time. I mentioned that before, that Plutus uses real time, POSIX time, and the underlying blockchain, the Cardano blockchain, uses slots. So you somehow have to convert between slots and time, and the slot config allows you to do that. So it tells you how long a slot is and at what real time the blockchain started, the first slot happened. And finally, we have the fee configuration, which tells you the constant fee of a transaction in Loveless. And in addition to that, this factor that scales how expensive script execution is in comparison to this constant fee. So in order to play with this a bit, let's start a REPL and import Plutus trace emulator and also data.default. And if we look again at this type of the emulator config, we see in particular it's an instance of the default class. That means we can use the default def method of that class to get a default emulator config. And so here we see, I believe it's 10 wallets. So by default, this initial chain state uses the left constructor, which, as I explained earlier, specifies an initial distribution for a number of wallets. So I think this is 10 wallets, and each of them has 100 ADA. So that goes until here. Then the second component, the slot configuration. So that says a slot is 1000 milliseconds long, so 1 second. And this is the time when that default blockchain started. I have no idea what that actually is, that time. Probably when Cardano launched. Finally, the fee config. So it says that each transaction has constant cost of 10 loveless per default. I mean, the actual transaction fees are much higher on the real blockchain. And the script fee factor is 1. So in order to try it, so recall we want to use run EmulatorTrace. So we need a config. There we can take the default config. So just def. And now we need an emulator trace. And I haven't explained yet how to write emulator traces. But I have told you that emulator trace is a monad. So without knowing anything specific about emulator traces, you all already know how to write certain emulator traces. For example, because it's a monad, we know it supports return. So we can use return to construct emulator traces without knowing anything else about the emulator trace monad. So the simplest emulator trace that we can possibly write is the one that immediately returns unit. So it doesn't use any of the special features of emulator traces, doesn't do anything on the blockchain, doesn't submit any transactions. It immediately returns unit. So this should work, and if we try it out, we see lots of data. It's quite overwhelming, and this is mostly due to this first return value here. I mean, we get a triple, the emulator events, maybe an error, and the emulator state. And most of this data that we see on the screen is caused by all these emulator events. So even in a simulation that doesn't do anything, we already get this overwhelming amount of data, which means that run emulator trace is not really a good way, a feasible way to try out contracts in your REPL, because you simply get too much information. Luckily, there is another function called run EmulatorTrace IO, and the type of that is simple. So it doesn't take a config, it just uses the default configuration, and it doesn't have this pure signature, so it doesn't just return this triple, it runs in IO. So let's try that out. Run EmulatorTrace IO, again with our trivial trace that doesn't do anything. And now the result is much more manageable. So we see right in the beginning a transaction gets validated. That is the Genesis transaction that distributes the initial funds. So that gives the 100 ADA to the 10 initial wallets. And then we see there's a wait of 2 slots. And then we get the final balances. And because we didn't do anything in this trace, we didn't submit any transactions, we immediately returned unit. Each of the 10 wallets still has their initial funds of 100 ADA. Sometimes, of course, you do want to specify an emulator config. For example, if you want to use different initial funds or more or less wallets. And there's a variation of this run emulator trace IO. It's called run emulator trace IO prime. And this takes two more arguments in addition to the trace itself. So it takes an emulator config and it takes a so-called trace config. So using the second argument, we can, for example, specify a different initial distribution. And let's look at this trace config type. So this has two arguments. The second one is a handle, and a handle can either be standard out or standard error, so the console, or it can be a file handle. So by using a different handle here, you can write this output in a file instead of just displaying it on the console. And the first argument takes emulator events or emulator event primes and returns a maybe string. And this works as follows. We have this long list of events, this overwhelmingly long list of events, and this first argument here allows you to filter those. So whenever you are not interested in an event, you can return nothing, and when you are interested, you can return just a string that formats this event in the way you want to see it. And by using this, you can influence which of the events you see and how they are displayed. Now let's look at a more interesting trace. And for that, I copied the vesting contract from last week into this week's code folder. And here I'm defining a trace in the EmulatorTrace monad that more or less reproduces what we did in the playground last week. And once I have this trace using this run EmulatorTrace IO function that I just demonstrated, I define this test function that will then actually run the trace and display the result on the console. So I'm using do notation, and in the playground we can just in the simulator tab start calling endpoints. In EmulatorTrace, before you can call an endpoint, you first have to start the contract itself. So we have to start this endpoints contract that we defined. And for that, there's a function called activate contract wallet. And that takes two arguments, the wallet on which to activate this contract, and then which contract. So we saw this known wallet before when we tried to find out the payment public key hash of a wallet. So I start the contract, the endpoints contract, for both wallets that I'm interested in, wallets 1 and 2. And the result is a so-called handle. It's a different type of handle than the handles I mentioned earlier, where I talked about file handles. But this is also called handle, it's a contract handle. So using do notation, so this is a monadic action in the EmulatorTrace monad that will have the side effect of starting this contract and returns me a handle, which will allow me later to reference to this contract. Same for the second wallet. So at this point in the simulation, both wallets run this endpoints contract that I defined last week. So now in order to call an endpoint, there is a call endpoint function. And I have to specify which endpoint to call, and that uses some advanced Haskell, again, type level Haskell. So this is a so-called type application that's activated with this extension here. So then I can use this add symbol and then a type. And this is a type level string. So the GIF endpoint, so it's not a normal Haskell string. This is actually a type, the type of this endpoint. So call endpoint and the name of the endpoint like this with the add symbol. Then the handle that we got. So this means I'm calling this endpoint on wallet 1. and then the parameters that this endpoint takes. So the GIF endpoint, if you recall from last week, took parameters of type GIF params, which had 3 fields: the beneficiary, the deadline, and the amount. So wallet 1 wants to make this gift to wallet 2. So the beneficiary will be the payment pub key hash of wallet 2. And like last time, I can get to that like this. So I have known wallet 2, and then there's this function mock wallet payment pub key hash. Then for deadline, let's say I want to wait for 20 slots. So as before, using this function slot to begin POSIX time def 20, I can get that. So def will work, because if I then later use run EmulatorTrace IO without any special configuration, then it will be the default configuration, and that's also what this uses. So that fits together. And finally the amount, so this should be 10 ADA. So at this point I'm calling that. Now I wait a bit, so I wait for slot 20 until the deadline has passed. And now the second wallet, so using the second handle that was bound against here, calls the grab endpoint, and if you recall, the grab endpoint only had unit parameters, so didn't take any parameters. So I can just grab, and I wait another 2 slots, and then I lock. So we know we can lock from inside the contract monad, so from inside the off-chain code, but we can also lock in this EmulatorTrace monad. So that's what I imported here from control monad freer extras. There is this log info function, and that takes a string. So I can just say, okay, I reached this slot S. So this wait until slot and the wait n slot both wait. So wait until slot, as the name suggests, waits until the given slot and returns the slot. So the return value of this would be 20, but we're not interested in that. So I'm using void, which comes from data functor, which ignores the result. So it turns the 20 that I get here into a unit. If I didn't use that, then the compiler would warn me that I'm ignoring a result of type slot. And this wait n slots, as the name also suggests, waits for a given number of slots. So it waits for 2 more slots. And then I lock this result. So we can try this out in the REPL. Let's call test from the REPL. Okay, and we see again first the Genesis transaction that distributes the initial funds. Then here we see that the GIF endpoint was called, some information about the parameters, then information about the actual transaction that was created. Now here, this log comes from the contract itself. So that is defined in the vesting module. If you recall, we saw that also in the playground. So this made a gift of so and so many Loveless to so and so. That comes from the contract. Then we see there's lots of waiting. And then here, slot 20, we see the endpoint call to grab. Then we see the resulting transaction. We see the action was actually submitted. Slot 21, slot 22. This is the log from the EmulatorTrace monad, the last line, reached slot 22. This is the log coming from the contract monad, from the vesting contract itself, collected gifts. And we see the final distribution of funds. In particular, we see that this wallet here now has roughly 10 ADA more than before, and this wallet here has roughly 10 ADA less. So this must be wallet 1 and this must be wallet 2. I have no idea why they are sorted weirdly. I assume they are sorted by their public key hashes and not by wallet 1, 2, 3, 4 until 10. So it seems to work. We can also see what happens if something goes wrong. So for example, if we don't wait until slot 20 when the deadline has passed, but for example only until slot 10, and try this again, then it shouldn't work. We see in the initial funds indeed this one wallet, so the gift is still out there. Wallet 1 still only has 90, but the other one, wallet 2, didn't receive the gift, so the grab didn't work. And we also see here, okay, no gifts available. So that comes from the contract monad. So in the off-chain code of the vesting contract, of the grab endpoint, we checked for available gifts where the deadline had already passed, and so we realized that the deadline has not been reached yet, so we don't even try to collect the gift. So this seems to work, and we see we basically get the same information that we also would get in the playground. Of course, we don't get the nice graphical overview over the transactions. But for that, it's much more lightweight. We don't have to start the playground server and the playground client, and we don't have to by hand set up the simulation. So we can compactly do it in code.